Electricity is an invisible force. To do actual work, to light our homes or power our modern world, it requires a continuous pathway to travel along. We call the materials that easily allow this electrical flow to pass through them good conductors. Copper and aluminum wire do this perfectly, completing a circuit with almost zero resistance. On the flip side, materials like rubber and plastic block that flow entirely. They are poor conductors, which is exactly why we wrap our electrical wires in them to keep that energy safely contained. This brings us to a safety rule we've all heard since childhood. Never touch an electrical switch or appliance with wet hands. But if you take a standard circuit tester and dip the exposed pins into a beaker of pure, completely distilled water, nothing happens. The circuit breaks. The bulb stays dark. That creates a paradox. If perfectly pure water is actually a poor conductor of electricity, why does getting your hands wet suddenly turn them into a massive electrical hazard? The hazard doesn't actually come from the water itself. It comes from something entirely invisible hiding inside it. The water we interact with every day, whether it's pouring out of a kitchen tap or sweating through our skin, is never perfectly pure. It is packed with dissolved minerals and salts. When salts dissolve in water, they break apart into freely floating positive and negative particles. We call these free ions. When an electric current hits the liquid, they align to ferry energy across the gap. Any liquid containing these ions is known as an electrolyte. You can test this by dropping an LED circuit into different household liquids. A heavily salted glass of water will make the LED glow brightly, while fluids with fewer ions, like vinegar or lemon juice, will produce a much dimmer light. The simple presence of free ions is the singular factor that turns a liquid from an electrical insulator into a highly conductive pathway. When an electric current flows through a liquid or biological material, it acts as an agent of change, triggering physical and chemical transformations in the substance itself. Look at this setup. If you run a continuous current through a standard potato for half an hour, you'll see a greenish-blue spot form right around the positive wire. The current is chemically altering the potato itself. In the late 1700s, scientists like Alessandro Volta began to realize that if an electric current could cause a chemical reaction in a biological material or a liquid, the entire process could be run in reverse. This is a model of what Volta eventually built. By stacking two different types of metal and separating them with layers of cloth soaked in an electrolyte, he created the world's first stable, continuous source of electricity. You can replicate this exact same mechanism using simple glass bottles. By inserting a zinc strip and a copper strip into a dilute acid, the chemical reaction between the metal and the electrolyte produces enough current to light an LED. Electrolytes provide the chemical engine required to generate and store portable power. Once you know how a battery generates current by dissolving metal into a liquid, you can use an external power source to deliberately drive that metal wherever you want it to go. To coat an object like an iron key, hook it to a battery's negative terminal. Attach solid copper to the positive terminal, and submerge both in an electrolyte. The current forces positive copper ions to physically bond onto the iron key. We call this electroplating. What started as small laboratory experiments in glass beakers was quickly scaled up to massive industrial operations, changing modern manufacturing. The main practical value of electroplating is protection. It allows engineers to take inferior, easily rusted metals and wrap them in an invisible shield against atmospheric moisture and oxygen. Look at the bumpers on classic cars. To survive the elements, that iron is plated with highly resilient metals like chromium, blocking the corrosion completely. There is also a secondary, purely aesthetic use. Electroplating allows manufacturers to take dull, inexpensive base metals and coat them with incredibly thin layers of highly valuable materials. This is how everyday tableware can feature a surface of genuine silver or gold without the weight or price tag of solid precious metal. Understanding how a single ion moves through a liquid provided the mechanics to store energy and protect the metals that build our world.